Right now, as you watch this, water molecules on your skin are escaping into the air at room temperature, not boiling temperature. Right now, at whatever temperature it is wherever you are sitting. They are leaving. Not all of them. Just the fast ones. Just the ones with enough energy. And here is the part that should stop you cold. You are built the same way. Most of you stays. But parts of you, the fast parts, the ready parts, they are always on the edge of becoming something else entirely. Physics isn't just a science. Sometimes it's a mirror. I want you to stay with that image for a moment before we go any further. I want you to actually feel it, not just understand it as an idea, but feel it as a physical reality. Because it is a physical reality, there are molecules leaving your skin right now. Not because you're hot, not because you're under pressure, not because something dramatic is happening to you. Just because, at this temperature, at this ordinary, unremarkable Tuesday afternoon temperature, some of them happen to be moving fast enough. And when something is moving fast enough and it finds itself close enough to the edge, it goes, quietly, without announcement, into the air. And I've been thinking about that fact my entire adult life. Not obsessively. I have other things to think about, believe me. But it comes back to me. It comes back to me every time I watch a puddle shrink on a cold morning. Every time I hang a wet towel and come back an hour later to find it dry, even though the room was cool and nothing dramatic occurred. Something left, something changed, and no crisis was required to make it happen. I want to talk to you today about why that matters, not just as a piece of physics, although it is a beautiful piece of physics, and I promise we're going to dig into the actual science and it's going to be worth it, but as something that has everything to do with how you think about change, how you think about becoming, how you think about whether you need the temperature to be turned all the way up before the thing you want to happen in your life is allowed to happen. Because here is what most people believe, and most people believe it so deeply that they've never even examined it as a belief. They believe that transformation requires extremity. They believe that real change, meaningful change, the kind of change that actually shifts who you are and how you move through the world, requires a boiling point. It requires a crisis, a rock bottom, a situation so uncomfortable, so untenable, so hot that you are finally forced to do the thing you've been avoiding doing. And until that moment comes, until the heat is high enough, you wait. You stay, you remain in the liquid state, and you wait for the boil. And I want to tell you today that that belief is incomplete. Not wrong, incomplete. And that difference matters enormously. Because the incomplete version of the story teaches you that you are at the mercy of temperature, that you cannot change until your circumstances demand it, that you are passive matter, subject to external forces, with no agency in the timing or nature of your own transformation. And the complete version, the one that the physics actually gives us, says something far more interesting and far more humanizing than that. It says that transformation is probabilistic, not conditional. It says that at any temperature, at any moment, in any season of your life, some part of you is already moving fast enough to escape. And your job, your actual, real, meaningful job, is not to generate a crisis. It's to understand the physics well enough to get yourself to the surface. So that's what this video is about. We're going to learn some physics today. Real physics. The kind that would satisfy a curious 10-year-old and a doctoral student at the same time, because the best physics always works at both levels. And then we're going to follow that physics wherever it honestly leads us, which turns out to be somewhere quite personal, quite beautiful, and quite unlike what you've probably been told about how change works. Let me start with a story. Not about a person, not about a dramatic moment, about an object. About a glass of water, an ordinary glass of water sitting on an ordinary table in an ordinary room. Nothing special about it. No one is heating it. No one is blowing across it. The room is maybe 65, 70 degrees, and that glass of water is losing itself. Slowly, quietly, One molecule at a time, it is diminishing. It is becoming something else. And if you check on it tomorrow and the day after that, you will find it smaller each time, until eventually it is gone entirely, transformed completely, not into nothing, into vapor, into air, into the invisible, but gone from the glass nonetheless. Now, if you had asked me when I was first learning physics to explain that, I probably would have said something like, well, the water evaporates because of the ambient temperature and the vapor pressure differential, and I would have been technically correct, and I would have explained almost nothing. Because the technical explanation, if you stop there, misses the thing that makes it astonishing. And the thing that makes it astonishing is this: the water in that glass is not hot. The water molecules in that glass are not all moving at the same speed. They are not uniformly energized, uniformly agitated, uniformly ready to leave. Most of them, the vast, overwhelming majority of them, are just sitting there bumping into their neighbors doing what water molecules do, content in a molecular sense to remain water. But not all of them. And this is the key. This is the thing I want to build the entire conversation around. In any collection of molecules, any collection of anything that has a temperature above absolute zero, which is to say, any collection of anything that actually exists, the energy is not distributed equally. It never is. The energy follows a distribution. A spread. Some molecules are moving very slowly, some are moving at around the average speed, and some, a small number but never zero, always some, are moving much faster than the average. Much, much faster. And those fast ones, when they find themselves at the surface of the liquid, when they happen to be near the edge rather than buried deep in the crowd, they have enough energy to overcome the forces holding them in the liquid. They can escape. They do escape. Right now, at room temperature, at 65 degrees, at 40 degrees, at almost any temperature above freezing, they are escaping. I want to give you a picture for this, because physics without pictures is just arithmetic, and arithmetic without pictures is just symbols, and symbols without meaning are just noise. So, here is the picture. Imagine a massive crowd of people, millions of them, so many you can't see the edges of the crowd, and they're all packed together in a giant swimming pool. Not swimming, just standing there waist-deep in water, all pressed together, all bumping into each other. And they're all moving a little. Some are nearly still, barely shifting from foot to foot. Most are moving at a medium pace, jostling, nudging, doing the ordinary shuffle of a dense crowd. But scattered through this crowd, randomly, unpredictably, not because they're special, not because they were chosen, there are runners. People who are moving fast. People who are weaving through the crowd with genuine speed and energy, who are heading, through no particular plan of their own, toward the edge of the pool. Those runners are your above-average energy molecules. The edge of the pool is the surface of the liquid. And when a runner reaches the edge, when a fast-moving molecule finds itself at the surface with enough kinetic energy to break free of the forces holding it in, it escapes. It goes into the air. It evaporates. It becomes vapor, and this is happening constantly, at every temperature. At every moment, the crowd is never still. The runners are always running, and some of them are always, perpetually reaching the edge. Now, and here is where I want you to really slow down and listen, when the fast ones leave, when the runners escape the pool, something interesting happens to the crowd they leave behind. The average energy of the remaining crowd drops, because the highest energy members of the system have just departed. The crowd becomes, on average, a little slower, a little cooler. And this is why evaporation cools things. It's not just that the water is leaving, it's that the hottest, fastest-moving parts of the water are the ones most likely to leave. And their departure pulls the average temperature of what remains downward. Your sweat doesn't just remove moisture from your skin. It removes your most energetic molecules. It takes the heat away with it, physically carries it off into the air, and leaves you cooler than you were, not because anything cold was applied, because the hot parts left. I find that remarkable. I find that genuinely, unexpectedly remarkable every time I think about it, which is often. You cool down not by adding anything cold, but by releasing what's running hottest inside you. The heat doesn't disappear, it doesn't get neutralized, it leaves, it transforms, it becomes something mobile and invisible, and free. And you, the system left behind, are cooler and calmer for its departure. I'm going to let you sit with the metaphorical implication of that on your own for a moment. I suspect you already feel it. I suspect there is something in your life that is running very hot right now. Some urgency, some restlessness, some part of you that is moving much faster than your average. And I suspect that part of you has been trying to escape for a while, and that you've been managing it back into the center, back into the average, because you don't quite trust what happens when it goes. We'll come back to that. But first I want to finish the picture, because there's more to this physics, and the rest of it is just as important, just as human, just as useful. So we have fast-moving molecules escaping the surface. We have the crowd continuously jostling and redistributing its energy, so that new fast movers are always being generated, because the energy doesn't just sit still, it's constantly being transferred and shuffled among the molecules through collisions, so that the identity of the fast movers changes constantly, even though the pool always has some. And we have evaporation happening quietly at any temperature. So why doesn't the glass of water evaporate instantly? Why does it take days or weeks for that glass to fully empty, even at room temperature? What holds the rest back? Two things. Two beautiful, important things. The first is called intermolecular forces, the attractions between the water molecules themselves, the thing that makes water want to be water, that makes the crowd want to stay together as a crowd, that makes the liquid cohere. These forces are real, and they're strong, relative to the energies of the molecules involved, and they act like hands in the crowd, holding people together, making it harder for any individual to push through to the edge, even if they have the energy to do so. The second thing is called vapor pressure, which is the counter-pressure exerted by the molecules that have already evaporated and are now floating in the air above the glass. Because here's the thing, evaporation is not a one-way street. The molecules in the air above the water are also moving around, also colliding with things, also subject to the same energy distribution. And some of them, when they collide with the surface of the water, get recaptured, get pulled back in, condense, return to the liquid state. So at any given moment, you have two simultaneous processes happening at the surface of that glass: molecules escaping the liquid, evaporating, and molecules returning from the air, condensing. The rate at which water evaporates and the rate at which vapor condenses are both happening constantly and simultaneously, and it's the balance between those two rates that determines whether the glass of water is actually getting smaller over time or whether it's reached an equilibrium where they cancel each other out. In an open room with good airflow, the vapor that escapes gets carried away. The concentration of water vapor above the glass stays low, and the rate of return is low. So the glass slowly but steadily empties over time. In a sealed container with no airflow, the concentration of vapor above the liquid builds up until the rate of return equals the rate of escape, and you reach what's called dynamic equilibrium. The surface looks still, nothing appears to be happening, but in reality there is an enormous amount of activity at the surface. Enormous numbers of molecules leaving and returning and leaving and returning. A constant invisible exchange that looks like stillness but is actually perpetual motion. I love dynamic equilibrium. I love it as a concept in physics, and I love what it means if you apply it to a life, because we tend to think of equilibrium as the absence of activity, as stagnation, as nothing happening, and dynamic equilibrium says, no. Equilibrium can be the most active state a system occupies. It can be full of departure and return, of escape and recapture, of constant exchange with the environment, and still appear, from the outside, to be doing nothing at all. Things that look completely static from a distance can be, at the surface, in a state of continuous and profound transformation. How many people do you know? How many times have you been this person yourself, who look from the outside completely stable, who appear to be in equilibrium, not changing, not moving, settled, and yet at the surface, at the interface between who they are and who they're becoming, there is enormous activity, enormous exchange, things leaving all the time, things returning all the time, the whole system in motion even though the glass looks calm. I think we catastrophically underestimate how much transformation is happening in people who appear to be still. And I think we catastrophically overestimate how much transformation is required to look dramatic in order to be real. Let me tell you about a concept in physics that I think is one of the most beautiful ideas in all of science. It's called the Maxwell-Boltzmann distribution. And it was worked out by James Clerk Maxwell and Ludwig Boltzmann in the 19th century, and it describes exactly the spread of energies in a collection of molecules. If you plot it, if you draw a graph with molecular energy on the horizontal axis and the number of molecules with that energy on the vertical axis, you get a curve, a beautiful asymmetric hump-shaped curve. Most molecules cluster near the average energy, creating a large peak in the middle of the graph. But the curve has a tail on the high energy side, a long, low, but never zero tail that extends out to very high energies. And it's the molecules out in that tail, the outliers, the statistically rare but always present high-energy molecules, that are responsible for evaporation. Now, here's what happens to that curve when you change the temperature. When you increase the temperature, the whole curve shifts to the right, the average energy goes up, and the tail on the high-energy side becomes larger and extends further, which means more molecules have enough energy to escape, which means evaporation happens faster. This is why water evaporates faster on a hot day than a cold one. Not because cold days have no evaporation. They do, it's just slower, but because the curve has shifted and there are more molecules in the tail. And here's what I want you to understand about that tail. It is never zero. At any temperature above absolute zero, at any temperature at which molecules are actually moving, there is always a tail. There are always some molecules with above-average energy. There are always some molecules that, given the right position, will escape. The tail shrinks as temperature drops, but it does not disappear. Not until you reach a temperature that is physically unachievable in any real system, a temperature so cold it would require removing every last quantum of energy from every particle in the system. Absolute zero, which nothing in the known universe has ever actually reached. So we live, all of us, all the time, in a universe where the tail is present, where the high-energy outliers exist, where escape is always, at every temperature, statistically possible. That is not a metaphor, that is the actual physics, and I am going to insist that you allow it to mean something. Because here's the thing about the way human beings think about change. We are temperature determinists. We believe, almost universally and almost unconsciously, that the amount of change we can produce in our lives is determined by the temperature of our circumstances. Hot circumstances, crisis, urgency, pressure, pain produce transformation. Cool circumstances, ordinary days, stable routines, adequate but uninspiring situations do not. And so we find ourselves in the position of the water in the glass, waiting for the heat to be turned up high enough, waiting for the boiling point, as though evaporation at room temperature were impossible. It's not impossible. You're doing it right now. Parts of you are in the tail right now. The question, and I want to make this very precise, is not whether you have any high-energy molecules. You do. You always do. The question is whether those molecules are at the surface and whether the conditions above the surface are favorable for them to actually escape. Let's think about what it means to be at the surface. In the glass of water, a high-energy molecule that is buried deep in the interior of the liquid, surrounded on all sides by other molecules, cannot evaporate no matter how much energy it has. It's too far from the interface. It would have to pass through too many neighbors, lose too much of its energy through collisions, before it could reach the edge. The molecule that evaporates is the one that is both high energy and close to the surface. Both conditions are required. Energy alone is not enough. Position matters. And in a human life, the analog of surface proximity is exposure, interface. The degree to which you are putting your most energized, most ready, most restless self into actual contact with the world outside your current state. A person can have enormous internal energy, enormous readiness, enormous capacity, enormous creative or intellectual or emotional power, and remain liquid indefinitely if they never put that energy into contact with anything that could draw it out. The surface has to exist. The interface has to be real. You have to actually be in the conversations, the rooms, the projects, the relationships, the situations where your fast-moving parts can reach the edge. This is something nobody tells you. Every piece of advice about change focuses on the energy side. Work harder, want it more, generate more urgency, raise your temperature. And sometimes that's the right advice, genuinely. Sometimes the limiting factor really is energy, and more energy is what's needed. But sometimes the energy is already there, already in the tail, already running at the surface escape threshold, and the limiting factor is that it's not near the surface. It's not in contact with anything. It's surrounded by sameness, by familiar resistance, by the comfortable interior of the liquid, where all the other molecules are exactly like it and reinforce its current state and provide no interface with the possible. If that's where you are, and I suspect it might be where more people are than realize it, then the answer is not to generate more heat. The answer is to increase your surface area, to find more edges, to be curious in more directions simultaneously, to show up in more places where you don't quite fit yet, where the people around you are moving differently, thinking differently, where there is a genuine differential between who you are and who you could be. Because that differential, that gradient, is what drives evaporation. Not heat alone. Gradient. A shallow, wide puddle on a flat surface evaporates much faster than the same amount of water in a deep, narrow container. Same volume, same temperature, dramatically different evaporation rate, because the puddle has vastly more surface area relative to its volume. More of the water is at the interface. More molecules at any given moment are close to the edge, and so the evaporation, molecule by molecule, proceeds much faster than in the narrow container where most of the water is buried deep and unreachable. Surface area, that's the lever most people never think to pull. They increase the heat, they increase the urgency, they boil themselves. And some transformation happens, it does. But nowhere near as much as would happen if they simultaneously expanded their surface area, if they spread themselves as a puddle spreads across more genuine interfaces with the world. Now I want to talk about something that I think is one of the most important and most misunderstood concepts in this entire discussion. And it's something that I feel is deeply unkind in the way we usually talk about it in human terms, even though the physics of it is completely neutral and completely beautiful. I want to talk about surface tension. Surface tension is the reason water beads up on a freshly waxed car. It's the reason water striders can walk on the surface of a pond without sinking. It's the reason a needle, if you place it very gently on the surface of still water, will float even though steel is much denser than water. It's a real force, a real physical phenomenon, and it comes from something quite specific and quite lovely. The molecules inside a liquid are attracted to their neighbors in all directions, above, below, left, right, in all three dimensions. They're surrounded, held, balanced. The net force on an interior molecule from all its neighbors adds up to approximately zero. It's pulled equally in every direction, so it goes nowhere. But a molecule at the surface has neighbors only on one side. The liquid side has almost nothing pulling back on it. So the surface molecule experiences a net inward force. It's pulled toward the interior of the liquid more than it's pulled toward the air. And this net inward force on all the surface molecules creates what we experience as surface tension, a kind of elastic film at the interface, a resistance to the expansion of the surface, a force that resists anything that tries to increase the surface area or break the surface. And in the context of evaporation, surface tension is one of the forces that must be overcome by a high-energy molecule before it can escape. The molecule has to break away from the attractive forces of its neighbors, and the surface tension is part of that resistance. So surface tension is, in a very literal physical sense, the thing that holds the water together, the force of cohesion, the thing that makes water be water rather than a cloud of disconnected molecules. Here's what I want to say about this, and I want to say it very carefully and very deliberately, because I think it's important. Surface tension is not the enemy. Surface tension is the signature of coherence. It is evidence that the parts of the system are in genuine relationship with each other, that they affect each other, that they are genuinely integrated into a whole rather than just being a loose collection of individuals that happen to be in the same place. A liquid without surface tension, without the molecules caring about each other at all, would not be a liquid. It would be a gas already. The cohesion is what makes the liquid state possible. And the liquid state is not a failure state than vapor. It is a different state with different properties and different capabilities. A liquid can flow in ways a solid cannot. It can take the shape of its container. It can carry things, dissolve things, participate in chemistry that neither a solid nor a gas can. The liquid state is full of capability. It's just different capability than the vapor state. Which means this: if you have resistance to change, if you have internal forces that hold you together and make transformation require energy, that is not evidence that you are broken or weak or stuck in the wrong way. That is evidence that you are integrated, that the parts of you are in relationship with each other, that you function as a coherent whole rather than as a scattered collection of disconnected impulses. The person who feels no internal resistance to anything, who has no surface tension, who changes instantly and completely at the slightest environmental prompt, is not enlightened. They are not fluid. They are scattered. They are not a liquid in the process of becoming vapor. They are vapor already, diffuse, directionless, responsive to every breeze. You are allowed to have surface tension. You are allowed to be held together by forces you don't fully understand and didn't consciously design. You are allowed to require energy to change. That requirement is proof of your depth and coherence, not your inadequacy. But the surface tension is not the final word. It's a force, and forces can be navigated, not always overpowered, not always with the violent boiling approach, but navigated. Found around. The molecule that evaporates at room temperature doesn't overpower the surface tension. It doesn't bulldoze through the resistance. It reaches the surface with enough energy that, at that specific interface, at that specific configuration of forces, it can slip through. Not because it forced the issue, because the conditions came together in the right way at the right moment, with the right energy. This is the difference, I think, between transformation that damages and transformation that heals. Both result in change. Both result in the molecule leaving the liquid, but the boiling approach, maximum heat, maximum pressure, force everything to change at once, that's violent. That's disruptive not just to the molecules that leave, but to the entire structure of the remaining liquid. It creates turbulence. It creates disorder. It often damages the container. Whereas the room temperature evaporation approach, patient, probabilistic, one molecule at a time, finding the surface rather than forcing the issue, that's quiet. That's elegant. The glass doesn't shatter. The remaining water continues to function. And the transformation still happens fully and completely, just more gently, just more slowly, just one molecule at a time rather than all at once. I have spent a lot of time thinking about which kind of transformation is actually better. And I genuinely think, not as a physicist, but as a person who has lived a life and watched other people live theirs, I think we have dramatically overvalued the dramatic kind and dramatically undervalued the quiet kind. We celebrate the people who hit rock bottom and came back. We make movies about the crisis-driven transformation, the moment of peak heat, the boiling point that produced the breakthrough. And those stories are real and they are meaningful. But they are not the only way. And they are not, in my experience, even the most common way. The most common way is the puddle on the cold sidewalk. Quiet, unhurried, one molecule at a time. And then one day you look, and the person is different, the life is different, and you can't quite point to the moment it happened, because it happened at room temperature, without announcement, at the surface, one escape at a time. Let me tell you about something else that happens in this system that I think is profoundly important and profoundly underappreciated. We've talked about evaporation, molecules leaving the liquid and entering the vapor phase, but I haven't talked much about what happens to those molecules once they're in the air. And what happens is this: they don't all stay there. Some of them come back. When a water molecule enters the vapor phase, it doesn't enter a static, unchanging state of freedom. It enters a dynamic environment full of other molecules, full of collisions, full of its own energy distribution. And some of those vapor phase molecules, when they collide with the surface of the liquid, get recaptured. They lose enough energy in the collision that the surface forces can grab them back. They condense, they return to the liquid. And here's what we do with that fact. In human terms, we call it failure. We call it going backward. We call it not being ready, or not being strong enough, or relapsing or regressing. Someone tries a new version of themselves, leaves the liquid, enters the vapor, becomes something lighter and faster and freer, and then the environment is not quite right, or the energy runs out, or the collision with the world is just a little too much, and they condense back, and we say they failed. We say they weren't really ready after all. And physics says, you are completely misreading what just happened. You are pathologizing a process that is not only normal, but necessary. Condensation is not the opposite of evaporation. Condensation is part of the same process. The molecules that return from the vapor phase bring energy back into the liquid. They increase the activity at the surface. They have, in the course of their brief vapor phase existence, collided with other vapor molecules, exchanged energy, experienced a different state, and they carry that experience back into the liquid with them. They are not the same molecules they were before they left. They are more experienced. They have more information about the vapor state, and their return does not undo the transformation. It enriches the remaining liquid with knowledge of what exists beyond the surface. I think about this every time someone tells me about something they tried and came back from, every course they took and quit, every relationship they entered and left, every project they started and abandoned, every version of themselves they tried on and returned. And instead of hearing failure, I want to hear what the molecule carries back, what they brought back into the liquid from their brief time in the vapor, because it's never nothing. It's never a pure return to the original state. Something came back different. And here's the deeper truth, the one I find most beautiful and most consoling. A system that only evaporates is not healthy. It's drying out. It's losing itself. A system that only condenses is stagnant and cannot change. But a system in dynamic exchange, where things are leaving and returning and leaving again, where the surface is constantly active, where the balance is alive and moving, that system is vital. That system is alive in the deepest physical sense of the word. Vitality is not about permanent escape. Vitality is about perpetual exchange. So, if you have tried things and returned, you are not a failure. You are evidence of a vital system. You are evidence of a surface that is active and engaged and exchanging with the world. And the question is never whether you should have left in the first place, or whether you were wrong to come back. The question is, what did the molecule carry home? I want to shift gears now, not dramatically, not away from the physics, but deeper into it, because there's something I haven't addressed yet that I think is the most practical thing I'm going to say today. And it's this: probability is not passive. I've been talking about probability since the beginning. The probability that a given molecule will evaporate, the probability distribution of molecular energies, the statistical nature of evaporation as a process. And I want to be careful that this doesn't sound like I'm saying everything is random and there's nothing you can do, and you just have to wait for the statistics to work in your favor. because that's not what the physics says. The physics says something much more empowering than that. The probability that a given molecule will evaporate depends on several specific, identifiable, influenceable factors. Not just one factor. Several factors, and every one of them can be changed. Let me go through them. The first factor is kinetic energy, how fast the molecule is moving at any given moment. In the glass of water, this is partly determined by the temperature of the whole system, but it's also subject to moment-to-moment fluctuations from collisions with neighbors. A molecule can gain energy from a collision and find itself briefly with enough energy to escape even if its average energy is below the threshold. In human terms, this is your immediate state. How rested you are, how clear your thinking is, how much creative or emotional or physical energy you're actually bringing to this moment. This is the most obvious lever, the one everyone focuses on, but it's only one of several. The second factor is surface proximity, how close the molecule is to the liquid-air interface. A molecule deep in the interior cannot evaporate regardless of its energy. In human terms, this is your positioning. Are you putting yourself in situations where your actual capabilities interface with real possibility? Are you in the conversations where your ideas can actually meet the people and circumstances that could draw them out? Are you near the edge of something, or are you buried comfortably in the interior of your existing world? The third factor is the local vapor pressure above the surface, the concentration of already evaporated molecules in the air immediately above the liquid. If that concentration is high, the rate of return is high and the net evaporation is slow. If the concentration is low, if the vapor is constantly being carried away by wind or ventilation, the rate of return is low and net evaporation is fast. In human terms, this is the saturation of your environment. If you are surrounded by people who are already fully embodying the change you're trying to make in yourself, there's no gradient anymore. The differential has collapsed. You feel no pull toward the surface because the vapor above you is already full of what you're trying to become. This is not a bad thing in every context. Sometimes you need that kind of environment to consolidate a change you've already made. But if you're trying to make a new change, you often need an environment where you are still novel, where you are the one bringing something that the immediate environment doesn't already have in abundance, where there is still a gradient to draw you out. The fourth factor is the actual surface area of the liquid. How much of the water is at the interface? Larger surface area, faster evaporation, all else equal. In human terms, this is the breadth of your exposure, the number of genuine interfaces you have with the world, the variety of contexts in which you appear and engage and show up, the range of conversations, projects, communities, and experiences that you actually participate in. A person who lives deeply in one context, however enriching that context, has a small surface area. A person who moves through many genuine contexts has a large surface area. And all else being equal, the larger surface area produces more evaporation, more transformation, more of the liquid at the edge at any given moment. The fifth factor, and this one is subtle, and I want to be precise about it, is what physicists call the sticking coefficient. When a vapor phase molecule returns to the surface and makes contact with the liquid, it doesn't automatically recondense. There's a probability for each collision that it actually gets recaptured rather than bouncing back off. The sticking coefficient is a measure of how receptive the surface is to the returning molecule. And in human terms, I think this maps onto something like openness, the degree to which you actually integrate the experiences you have rather than bouncing off them. The degree to which the things that happen to you stick, change you, inform the next version of your surface. A person with a high sticking coefficient, metaphorically, is someone who learns from their experiences, who allows their brief excursions into new territory to actually change the surface they return to. A person with a low sticking coefficient returns from every experience essentially unchanged, because nothing quite sticks, because the surface is always the same regardless of what comes back to it. 5 levers, Kinetic energy, surface proximity, vapor pressure gradient, surface area, sticking coefficient, and not one of them is fixed. Not one of them is outside your influence. You cannot change all five simultaneously, and you don't need to. Moving any one of them meaningfully changes the probability of evaporation. Moving two changes it dramatically. Moving three changes it in ways that begin to feel, from the inside, like a completely different kind of life. The reason I find this so important is that it gives you something specific to work with. Not try harder, not want it more, not generate enough urgency. Those prescriptions all address only the kinetic energy lever, the first of the five. And kinetic energy, while real and important, is the lever that depletes fastest and recovers slowest. It's the most expensive lever to pull, and it's the one that, pulled in isolation without attention to the other four, produces exhaustion more reliably than it produces transformation. The cheaper levers, cheaper in the sense of requiring less energy to pull, producing more effect per unit of effort, are positioning and surface area and environment and integration. These are the levers that most approaches to change almost completely ignore, and they are, in my experience, both as a scientist and as a person, the ones that produce the most durable and surprising results. Let me give you a concrete example. Suppose you want to learn something new, something genuinely difficult, a skill, a way of thinking, a practice that requires sustained effort over a long period. The kinetic energy approach says, want it badly enough, work hard enough, discipline yourself ruthlessly, create enough urgency through deadlines and accountability and consequences. And yes, some of that is necessary. You do need to actually do the work. But if that's your only lever, you're the deep, narrow container. You're working against your own resistance with raw heat. The surface area approach says, find as many genuine contexts as possible in which this skill matters, and in which you are slightly out of your depth. Not completely out of your depth. That's too far from the surface, too much resistance, the molecule never gets through. But slightly, a little stretched, a little at the edge. Because in that position your learning is not a purely internal, purely effortful process. It's being drawn out of you by the differential between where you are and where the situation needs you to be. Evaporation by gradient rather than evaporation by heat. And it's remarkable how much more efficient that is, how much less effort it requires, and how much more result it produces. Now I want to talk about something that I've been circling around this whole time and that I think is actually the heart of what I'm trying to say. I want to talk about the nature of temperature itself, because I've been treating temperature as a given, as something that happens to a system from the outside, as an environmental condition. And that's accurate enough for a glass of water. But it's not the full story, even in physics. And it's definitely not the full story in a human life. In a physical system, temperature is a statistical property. It describes the average kinetic energy of all the molecules in the system. It's a collective property, a property of the whole, not of any individual part. No single molecule has a temperature. Temperature is what emerges when you have a large number of molecules interacting with each other, and you ask, on average, how much energy are they carrying? Temperature is an average. It is, in the most precise possible sense, a generalization. And here is what this means. When someone says to you, when life says to you, when circumstances say to you that your temperature is low, that you're in a cold season, that nothing is happening, that you're in a stagnant period, they are telling you the average. They are not telling you about any individual molecule. They are not telling you anything about the tail of the distribution. They are telling you the middle of the graph, the peak of the curve, the most common state of the most common parts of you. And they are saying nothing whatsoever about the outliers, the high-energy molecules, the ones in the tail, the ones that are already, right now, at or above the escape threshold. You have never, in your entire life, been purely average. There is not a moment in your history when every part of you was exactly at the mean. The mean is a mathematical artifact. It doesn't exist in any molecule, it exists only in the aggregate description of all the molecules together. You, the individual, are always either above or below it in any specific aspect of your energy, your capability, your readiness. And the question that the physics asks, but that we almost never ask in ordinary life, is not, what is your average? The question is, which parts of you are in the tail right now, and are they near the surface? I think this is one of the most liberating ideas I've ever taken from physics into the way I think about people, including myself. The idea that the temperature, the average, is not the limit. The tail is always there. The high-energy outliers are always present. The question is only whether they're positioned to do anything. Let me tell you about a principle in physics that I think is underused in ordinary thinking. It's called ergodicity, or really the lack of it. The idea that in many real systems the individual trajectory through phase space is not the same as the average behavior of the ensemble. In simpler terms, the average behavior of 1,000,000 people is not an accurate description of the individual journey of any one person. You are not a statistical average. You are a specific, particular, non-average instance of a human being, moving through a specific trajectory in time, with a specific energy distribution that is yours and not anyone else's. And the statistics that describe what most people do in situations like yours, the aggregate, the average, the temperature of the system, those statistics are useful for some things and completely useless for others. They are useless for predicting what you specifically will do. They are useless for telling you what you're capable of. They are useful only for telling you what most people do, which is interesting but not constraining. You are not bound by the temperature of the system you're in. You are one molecule in a large crowd, and the crowd's average energy does not determine your individual energy, your individual position, or your individual probability of reaching the surface and escaping. I want to stay with this for a moment and make sure it lands, because I think it's being heard correctly. I am not saying that circumstances don't matter. They do. The temperature of the system affects the entire distribution. It shifts the whole curve, tail and all. Cold circumstances make every molecule slower on average, including the fast ones. I'm not dismissing the reality of difficult circumstances or pretending that environment has no effect on what's possible. Environment absolutely affects what's possible, but it does not determine it absolutely. It shifts the probability. It does not eliminate the tail, and the tail, the fast-moving, above-average energy, surface-adjacent molecules, those are always there. Always. And they are what evaporation is made of. So if you're in a cold system, if the circumstances of your life right now are not particularly hot, not particularly energizing, not particularly conducive to dramatic transformation, what the physics tells you is not, wait for better circumstances. What the physics tells you is, find the tail, find the parts of yourself that are right now above average, and find the surface. Find the interfaces where those above average parts can actually meet something beyond the current boundaries of who you are, and give them a chance to escape. That's it. That's the whole instruction. That's the room temperature evaporation protocol. Find your tail, find your surface, give the fast molecules a chance to reach the edge. Now, let me get very practical. Because I've been a physicist my whole career, and I believe in the practical application of theory. Theory without application is beautiful but useless, like a formula you can write but not compute. So I want to give you some actual things to do with all of this. Not many things. 3 simple practices, each of which addresses a different lever in the evaporation model, and any one of which you could begin right now, today, at room temperature, with exactly the circumstances you currently have. The first practice I'm going to call the surface inventory, and I'm going to ask you to do it once a week, not every day. Once a week is enough. More than once a week might actually be counterproductive. You'll start monitoring rather than living, and monitoring from the inside changes what you're monitoring. So once a week, sit down somewhere quiet with something to write on and answer 3 questions. Not in depth, not with elaborate reflection, just honestly, briefly the way you would answer if someone was paying attention and you didn't want to waste their time. The first question is, where am I actually at the surface right now? Not where do I wish I were at the surface. Not where I think I should be putting my energy. Where are the places in my actual current life where my real energy is in genuine contact with new possibility? Where am I slightly stretched? Where am I at an edge, even a small one? Name them. 2 is enough. 1 is enough. If you can't name any, that itself is important information. It means your surface area may need expanding, which is a specific and actionable diagnosis. The second question is, what's happening with my vapor concentration? Look at the environments you actually spend most of your time in. Are the people and contexts around you already fully saturated with the kind of person you're trying to become? If so, the gradient has collapsed and the pressure to change is low. This is not a judgment of those people or those environments. It's a physical observation about gradients. You may need to add some contexts where you're still novel, still slightly out of your element, still bringing something that isn't already abundant in the room. The third question is, what condensed recently that I called failure? Name one thing from the past month, one attempt, one excursion, one brief evaporation into something new that ended in a return. And instead of filing it under failure, ask, what did the molecule carry back? What do you know now about the vapor state, about the thing you were reaching for that you didn't know before you tried? What information came back into the liquid with you? Do that once a week. 3 questions. It takes 10 minutes. And over time, not dramatically, not at the boiling point, it shifts your relationship to the surface of your own life in ways that I think will surprise you. The second practice is what I'm going to call the probability stack. And this one is more targeted. You use it when there's a specific change you're working toward, a specific evaporation you want to achieve. Take that specific change and work through the 5 levers. For kinetic energy, what's one thing you can do this week, not this month, this week, to increase your immediate internal energy in this specific domain, not in general? Not some overall self-improvement project. What specifically makes you more ready, more clear, more alive to this particular possibility? Maybe it's sleep. Maybe it's removing a specific source of drain. Maybe it's spending an hour with something that genuinely energizes you and is related to this change, before you ask yourself to do the hard work of the change itself. For surface proximity, what's one situation you can put yourself in this week where your current energy will actually interface with this specific possibility? Not preparing to interface, not planning to be near the surface someday. One actual situation this week where your fast-moving molecules get a chance to reach the edge. For vapor gradient, is the environment around this specific change saturated or undersaturated? Do you need more exposure to people already in the vapor state you're reaching for to see that it's possible and feel the pull? Or do you need less? Do you need to step back from environments where you're constantly comparing yourself to people already there? Because that comparison is creating a kind of pressure that pushes you back into the liquid? For surface area, what's one way to expand your exposure to this specific change? One new context, one new conversation, one new way of engaging with the territory you're trying to enter. And for the sticking coefficient, what helps you actually integrate experiences in this domain rather than bouncing off them? For some people, it's writing. For some, it's conversation. For some, it's silence and reflection. What's the practice that makes new experiences actually change you, rather than just passing through? Pick 2 of those 5, just 2, work them this week, and then next week, reassess. The third practice is the one I think is most unusual, and most important, and most likely to be underestimated. I'm going to ask you to find a glass of water, room temperature or colder. Sit it somewhere you can see it. And for 2 minutes, just 2, watch it. Don't try to see the evaporation because you won't. It's happening, but it's far too slow and individual molecule for your eyes to detect. Just sit with the knowledge that it's happening. Just let yourself inhabit the fact that transformation is occurring right now in that cold, ordinary, undramatic glass, without any crisis, without any special conditions, without anything being forced or broken or pushed to its limits. And then ask yourself, not out loud, not in writing, just as a quiet internal question that you don't need to answer, what's leaving right now? Not what do I want to leave? What's actually, already quietly, on its way out? What part of my old self is already evaporating, at room temperature, in the ordinary conditions of this ordinary day? You don't need to answer the question alone changes the surface. The question alone is a kind of evaporation. It takes a molecule of your attention and moves it toward the edge of something it hasn't been near before. That's enough. That's the beginning of everything. I want to come back now to where we started, because I think the journey is worth seeing whole. We started with water molecules on your skin, escaping at room temperature, quietly and constantly and without drama. We ended up here with 5 levers and 3 practices and a whole new way of thinking about what change requires. And I want to make sure the thread is clear, not just intellectually clear, but felt. Here is what I think we've established. Temperature is an average, and you are not an average. You are always in some part of yourself, in some domain, at some interface, above the threshold. The tail of the distribution is always present, at every temperature, in every season of your life. Your surface tension, your resistance, your cohesion, your internal forces of integration is not your weakness. It is proof of your depth. It is the signature of a self that is actually held together by genuine relationships between its parts, and transformation does not require you to destroy that. It requires you to navigate it. It requires a molecule with enough energy, close enough to the surface, at the right moment, not a crisis, not a boiling point, just a quiet arrival at the edge with enough energy to slip through. Condensation is not failure. Everything you've tried and returned from has left something in the liquid. Every excursion into the vapor state, however brief, has informed the surface you came back to. You are not the same liquid you were before those attempts. You are richer, more complex, more informed about the possible. And the exchange between liquid and vapor, the perpetual movement of departure and return and departure again, that is not stagnation. That is vitality. That is the most alive state a surface can be in. And you do not need to wait for the temperature to be turned up. You do not need a crisis. You do not need the heat to be high enough. You need to find your tail. You need to find your surface. You need to give the fast-moving parts of you a genuine interface with the world. And then, not all at once, not dramatically, not in a way that will make a compelling movie, you will evaporate. Molecule by molecule, quietly, at room temperature, in the ordinary conditions of a life that doesn't need to be extreme in order to be transforming. Here is what I want to leave you with. One image. Carry it with you if you want, leave it here if it doesn't fit, but let me offer it anyway. Somewhere near you, right now, there is a cold surface. A glass, a puddle, a window with condensation on it, a wet towel drying on a rack, something cold with water on it, and that water is evaporating, not boiling, not even warm, just quietly, constantly, molecule by molecule, becoming something else. It's been doing this the entire time you've been watching this video. It did it yesterday when you weren't watching. It will do it tonight when you're asleep. It requires nothing from you. No observation, no encouragement, no dramatic intervention. It just requires being water, at any temperature above absolute zero, with a surface exposed to the air. You are built the same way. The physics that governs that cold, quiet, ordinary evaporation is the same physics that governs you. You are not exempt from thermodynamics. You are subject to the same beautiful rules that govern every system in the known universe. And those rules say clearly and without ambiguity that transformation at low temperatures is not only possible, it is inevitable, given time, given surface, Given the perpetual, naturally occurring, never-zero presence of fast-moving molecules in any living system, you don't need to boil to become something new. You just need to be at the surface with enough energy at the right moment. And that moment, at every temperature, in every season of your life, in the coldest and most ordinary and most unremarkable circumstances you can imagine. That moment is always, statistically, already here, already possible, already happening somewhere at the surface of who you are, in ways too quiet for anyone, including you, to see. You were never frozen. You were just in a cold glass. And cold glasses evaporate too. If something in this video changed the way you see yourself, if something in the physics, or in the surface tension, or in the idea that condensation is not failure, landed somewhere real and useful for you, I would genuinely love to know which part. Leave a comment. Tell me the specific thing. Not because I'm fishing for engagement, because I actually want to know what reaches people and what doesn't, and that information makes the next conversation better. It makes the next glass of water more interesting to look at. And if this kind of thinking is something you want more of, if you like following the physics idea all the way into something personal and practical and a little bit strange, the subscribe button is there. No pressure, no urgency, no crisis required. Only the ones who are ready will click it. The ones who aren't yet will evaporate toward it eventually. That's not pessimism, that's just thermodynamics.